midterm, or not midterm, test one. In whatever class is a midterm. Okay. And of course, I'll take any questions about the practice test. But what I'm going to do first is, as a time saver, okay. So, okay. Now we have, based on the give a PDE that has homogeneous boundary conditions, or if it doesn't have homogeneous boundary conditions, but it's transform it so that it does. So either way, you could be in that situation, see separation of variables, that the boundary conditions must be homogeneous. And normally what you do is you figure out, based on the boundary conditions that you have, what is the form of your solution? Like your solution, you know, your solution is going to be an infinite sum of some coefficients that depend on time times some functions of x. And what are those functions of x? And we've seen certain functions that keep popping up because of certain boundary conditions that keep popping up. So as a quick reference guide and as a time saver on whatever problems you have, here's how it would play out. So we're going to assume that the domain of a PDE with the interval 0 to L in space, of course, equal to 0 for time. Okay, so I'll describe these the eigenfunctions are as follows. Now, the one we've probably seen the most often is Dirichlet of type 1 boundary conditions at both ends. So u of 0t is 0, u of lt equals 0. So then we have your functions xn of x is equal to sine of n pi x over L. So you're taking the width of the domain into account for, okay, so, oops, sorry, n starting at 1, not 0, because we have to have non-trivial solutions. Okay. Next, what if it's Neumann or type 3 boundary conditions? So u dx is 0 at both endpoints. Okay. Well, what should it be by contrast with the previous case?
Cosine.
Yeah, cosine, and the argument is the same, n pi x over L. What values of n?
Starting at 0.
Has to start at 0 because when n equals 0, cosine 0 is 1, so we do have a non-trivial solution in that case. All right. So here we have both cases of the simplest kinds of boundary conditions, where you have the same type of boundary condition at both ends. But we have seen problems where you have a different type of boundary condition at each end. So, for instance, suppose it's type 1 on the left and type 3 on the right. This is one that has popped up at least once. So the fact that it's equal to 0 at x equals 0, that tells you that it's going to be a sine. But the fact that it's you want the derivative to be 0 at the other end is going to affect which kind of sign. So sine n pi x over L will not work because it won't satisfy the condition at the right. So what you're going to have is sine of n plus a half pi x over L. And here we do need n equals 0, even though it's a sine function because of the 1/2. So the first function in sequence would be sine pi over 2 x over L, and so on. Okay. So then what happened is you take a derivative of this, you're going to get cosine of this times something. You plug in x equal L, and you're going to get cosine of an odd multiple of pi over 2, which is 0. So one more combination. What if it's du dx is 0 on the left side? And actually, I don't think this has popped up in any example that we've seen, but just for sake of completeness. So type 3 on the left, type 1 on the right. So you can think of the answer to this one as sort of a combination of some of the other cases that we have here. Anyone think of, even if it amounts to a guess, what do you think it should be?
The cosine n plus a half pi x over L.
Yes, it would be. All right. Because if you plug in x equal L, you want what's inside to be a root of cosine. And sure enough, it'll be an odd multiple of pi over 2. Whereas if you take the derivative of this and you get sine, you plug in x equals 0, sine of 0 is 0, and you get 0. Here too, you'd have to start at n equals 0 to make sure that you have a non-trivial solution. So, because if you look through the practice test solution, I was quite detailed as far as going through the whole separation of variables process. But that's just for your benefit to see where all the various steps come from. I would not expect you to write everything out in all that kind of detail when you're showing up the answers. So I'll be fine with you simply resorting to this list to obtain the form of your solution, and then just work everything else out from there. So this also takes into account that when you perform separation of variables, you need to have a non-trivial solution that satisfies the boundary condition. Because separation of variables, you have a function of x equals a function of t, therefore it's equal to a constant. And in the past, we've gone through these cases like, well, what is the constant, positive, negative, or 0, and we have to rule certain cases out based on not being able to get a non-trivial solution that also satisfies boundary conditions. So we're cutting through all that much. And you'll see from whatever examples we have, you'd have your spatial ODE to solve, and then your temporal ODE to solve. So the spatial ODE, the solution is going to be one of these.
What about type 2?
Okay, so I've not covered that case here. So in that case, at the boundary you'll have a linear combination of u and du dx equals 0. So there would be more work to do in those cases.
Okay.
But we saw an example of that where you had type 1 boundary condition on the left, type 2 boundary condition on the right. And it turned out that the eigenvalues, the lambda values, could only be known numerically. So in that case, you're not able to fully solve the problem anyway. All right. Okay. So as far as what you should be able to do, I'll do a quick rundown of different problems. So problems of this type you can expect to see, but when certain details change. So given a second order linear PDE this form, so you want to match it to this general form in terms of coefficients of uxx, uxy, uyy, if those terms are present. All other terms can be ignored for this case. To identify the coefficients a, b, and c, and therefore, and from both, determine if the equation is hyperbolic, parabolic, or elliptic. The equation we were dealing with the most, the heat equation, so ut equals a coefficient times uxx. That is an example of a parabolic equation. There'll be a problem of taking a verbal description of an IBVP and writing down the actual equations that constitute that IBVP. What is the PDE? And so I mentioned here you can use these generic coefficients like alpha squared in the heat equation with the appropriate spatial domain. The time is always going to be t greater than 0. Look for the verbal description for what is the initial condition. That also goes in the spatial domain. Actually, I'm going to add here. Whoops. Boundary conditions. Just to be rigorous, but apply for all t greater than 0. So from the verbal cues, what types of boundary conditions do you have? So the laterally insulated is just so that this PDE is valid, so you don't need any additional terms. Okay, because what we saw an example of variation in the heat equation that allowed for lateral heat loss, but that doesn't apply here. Okay. For instance, if one of the endpoints of a rod is insulated tells you type 3 or Neumann boundary condition. So here, if you have one of the endpoints is immersed in the medium of a given temperature, that's this kind of boundary condition. The other possibility that's not featured in this problem is if one end of a rod is at a fixed temperature, that is a type 1 boundary condition. So just making sure you're matching the verbal descriptions to the appropriate equation. Here we have a generic separation of variables problem with so homogeneous PDE, homogeneous boundary conditions, and some initial data. So based on what I showed you earlier, from the boundary conditions, in this case, capital L will be equal to 2. That will tell you what your spatial solution should be. So then that would tell you what this is. And then keep in mind how the separation of variables goes, that this value here, lambda squared, which is the eigenvalue, that goes into your temporal solution also. resulting in this exponential. So another way to think of it is whatever is multiplying the x. So here in your spatial solutions, it's sine or cosine of some constant times x. That constant, or really is minus that constant squared, is what goes in here. In this problem, we had this plain old ut equals uxx. There was no coefficient alpha squared here. If there is a coefficient, whatever that coefficient is, that would go in the exponential also. So that comes from what arises from separation of variables, these ODEs, where this one, for t, capital T, might have an alpha squared or whatever coefficient that the heat equation has. And these ODEs are associated with these general solutions. What's left is to figure out the coefficients a sub n. And that comes from, so this formula is what applies, that you have the integral over your spatial domain of whatever your initial data is, times your spatial solution, divided by the integral over your spatial solution squared. Now, I'll have a little more something to say about this integral momentarily. Now, depending on the initial data, the coefficient an might be relatively easy to work out. For instance, in this problem, the initial data is a linear combination of your spatial solutions. So figure out the appropriate values at n that go with it. But keep in mind, in this problem, it would not be n equals 1, n equals 4, not necessarily, because your spatial solutions are assigned, in this case, sine n pi x over 2, because the domain is the interval 0 to 2. So that means that we're looking at n equals 2 and n equals 8 are the cases where an is non-zero. So that's one thing to be careful about. And a lot of our examples, the spatial domain is 0 to 1, but what if it's not? So you have to keep that in mind. So then, because only these coefficients of the initial data are non-zero, what ends up happening is your solution u of xt closely resembles your initial data. It's just that each term in the initial data is multiplied by the appropriate exponential in time. And that ends up being your solution. Are there any questions about this problem in particular? Because it's been involved. This is what happened in this problem. I'm going to add something here, it's a shortcut. You have a following that because to get the coefficients an, you're evaluating in the denominator, you have the integral from 0 to L of x n of x squared. But that turns out to be equal to, for these cases where you have a sine or a cosine, turns out to be L over 2. Let's see. There's one exception. The second case, for n equals 0, the integral just turns out to be L. And the reason for that is, here, when n equals 0, your function is just 1. But for all other cases, it's a sine or a cosine. When you have a sine or a cosine squared, from the integral from a to b of sine squared cx, or some constant c. What do you do in that case? To evaluate the integral, use a half angle formula. Which gives you this. And from this term, you get b minus a over 2. Okay. Oh, you know what? I think I might have messed up here. Alright, so work out the rest of the integral. For sine. And that gets evaluated from a to b. Okay. All right, it definitely applies for the first two cases. I'm not doing these in my head. It's really not in the middle of class. When you're in the middle of teaching, your IQ plunges. I'm just not going to take that chance. But you would still use this trig identity. So what you have here is valid. So what happens when you plug in the limits a and b, which in this case would be from 0 to L. So, but anyway, this is something I can, again, save some time. And I've written this out for sine squared. Same thing applies for cosine squared. You just have a plus here instead of a minus. Yeah.
So what will we substitute in for A and B? Like 0 and L?
Yes.
Okay.
And the thing is, for these cases, you plug in 0 and L, you're going to have a sine of 0 for the lower limit, sine of n pi for the upper limit, so it's all 0. So these terms end up making no contribution to the integral in these two cases. In these cases, let's see. All right. Okay, we'll work it out in my head. So what happens here is you have sine of an odd multiple of pi over 2, but you have double the angle here. So now it's sine of a multiple of pi, integer multiple of pi times x over L. So actually, yeah, okay, so in all four cases, these terms end up just becoming 0. So, alright, so my original comment is correct. Okay. So what that means is, in this separation of problem like this one, we're working on these. Now, again, for some initial data, like in this problem, you don't actually have to evaluate the integral because the initial data is already a linear combination of these functions. But if you do have to do this, for example, suppose u of x0 is equal to x, so the integration by parts is involved. At least for the denominator, that's been worked out. Any questions about this one?
So we would just substitute in like u of x0 for like.
Yeah, whatever your given initial data is. Here, okay, non-homogeneous boundary conditions, you transform it so that boundary conditions are homogeneous, and then write down the new problem, which, depending on the boundary conditions, might result in an additional term for a PDE. Sure to pay attention to directions here saying you do not have to solve a problem, so don't waste time doing that. So this is all about just the transformation procedure. And really, you know what the new boundary conditions will be. They'll be the same as the original boundary conditions, except 0 on the right-hand side. But whatever boundary function you have is going to affect the initial condition and possibly the PDE also. So that's where I'll be looking to see if you get it right. Here, non-homogeneous PDE, homogeneous boundary conditions. So this is from lesson 9. So it deals with the method of Eigenfunction Expansions. So you need to know what the spatial solutions are from a homogeneous PDE that has the same boundary conditions. Because that's what you'll use in your Eigenfunction expansion. Those will be your eigenfunctions. So what you need to do is, your solution will have this form, where these are the spatial solutions from the homogeneous version of the PDE. You're going to have an expansion of your source term that has coefficients Fn, and then an eigenfunction expansion of your initial data. And all using the same eigenfunctions. The coefficients that you get from these tell you what your ODEs are. So your ODE will be something of this form. Now this expression may be different. It could be like n pi over L, or it could be n plus a half pi over L that goes here. Your source term coefficients go here. The coefficients of your initial data are the initial data for your ODEs. So what goes in here depends on the boundary conditions and your spatial domain. Once you have your ODE set up, you can jump directly to using this solution formula. So you just work out what that is. And then, once you have this, un of t for each n, you put that back in here, and you're done. That's where your final answer comes from. So you expand this, solve the ODEs that come from these values. The solutions of those ODEs go here. That's the workflow. All right. The only problems I have told. So I want to check on something here. Just make sure I'm getting correct information. Okay, yeah, because there are a total of 7 problems. Remember, for undergrads, you can choose one problem to not do. Right. So there are 2 problems that relate to the Fourier transform. So this one is where you'll have a problem on a semi-infinite domain, x going from 0 to infinity. You'll have some boundary condition at x equals 0, and then initial data. So based on the kind of boundary condition, you'll choose the appropriate Fourier transform, sine or cosine. Transform of PDE, you'll use a rule like this one. And then you'll also take the transform of initial data. So for this, you rely on the Fourier transform table, such as the one in the back of the book. So after transforming the PDE and the initial data, and transforming the PDE already takes the boundary condition into account, then you'll solve the ODEs, which depend on the Fourier variable omega. And then, so that will give you the transform of your solution. So then you substitute that into the appropriate inverse transform for whatever boundary condition you have. And there you have it. So the problem will state, the problem may state that you can leave the solution in integral form. And another Fourier transform problem, this one will be on the entire real number line. This is a Cauchy problem, so there are no boundary conditions. So like in the previous problem, you use appropriate transform for the PDE and the initial data, again using Fourier transform tables. So for instance, that's how this was obtained, straight from a table. And now you have an initial value problem, an ODE paired with the initial condition that comes from transforming the initial data condition of your original problem. And now you can solve these ODEs. Okay, that's given here. And then this will be substituted into the appropriate inverse transform. So that's what leads to this. And the scaling factor up front is combined with the scaling factor that's in the inverse transform, resulting in this constant factor of 1/2. And you're done. One thing you could do as you work through these problems, if time permits, you could simply take your solution and substitute it back into the original problem. Does it satisfy the PDE? Does it satisfy the initial condition? Does it satisfy the boundary conditions? If the answer to all of these is yes, and you haven't made any algebraic mistake along the way, then you have the right answer. Now that I've said something about each of these, are there any questions about them?
Would we need to state the boundary conditions we see, or just continue on with the problem? Like, don't bother with
care about the type. Yeah, you're just working with whatever boundary condition is given. Yeah, I never think in terms of type 1, type 2, type 3, and drawing on maybe just convention and textbook is using. The terms Dirichlet and Neumann are common usage for type 1 and type 3 boundary conditions respectively. As well as in the PDE community, that's how people tend to talk about those things. Yeah. Oh, okay. I do want to point out something that's come up from one of the homework problems. I need to unshare, reshare this. Okay, lesson 10, problem 3. There's a minor mistake in the problem. So it's kind of strange, actually. This is not the definition of the Heaviside function. The Heaviside function is equal to 0 for negative x, and then it jumps up to 1 at x equals 0 and stays 1 forevermore. So not what's described here. On the other hand, given the correct definition of the Heaviside function, the one I just told you, taking that Heaviside function of 1 minus x does give you the initial data for this problem. So, so the only actual mistake is this right here. As far as working out the problem, the easiest thing to do is think in terms of this graph. That you're dealing with initial data that's equal to 1 for x between 0 and 1, and then 0 after that. Because for the transforms that you're using, like sine or cosine, both of them involve, to take a transform, you're evaluating the integral that goes from 0 to infinity. Now, anytime you're taking a transform, if a function you're taking a transform of is equal to 0 on some portion of the domain, 0 to infinity, then what you can do is only integrate the non-zero portion and change the limits accordingly. So instead of integrating this function, Heaviside function of 1 minus x, from 0 to infinity, you can think of it as integrating 1, this portion, for the limits 0 and 1. Because what happens from 1 to infinity is irrelevant because the function is 0 over anyway. So then you have an integral that can be evaluated.
So is it H in general that we'd be replacing with, okay, so the mistake is that it's the Heaviside function is supposed to be 0 when x is less than 0 and 1 when x
Yes.
is greater than or equal to 0.
Right.
Correct? So up there it says u of x and 0 is equal to h of 1 minus x. Are we replacing that with the new definition and using 1 minus x, or are we replacing it with h of x?
Okay. It's still this, where h of x is not this, but the correct definition.
Okay.
Yeah. So strangely, that's something I actually went ahead and plotted the graph just to be sure that the correct Heaviside function evaluated at 1 minus x does give you this. But fortunately, you can actually work out the problem without caring what the definition of the even-side function is. And you just think that, oh, it's a function that's equal to 1 here and 0 everywhere else. Because the only time initial data plays a role is when you're taking its transform to get the initial values for your ODE. You really can forget about it. And yeah, there's a problem where for some reason they use a sine transform, I don't know why. In fact, it would be just plain wrong. You need to know value u is 0t, and you don't. Yeah, so I think whoever wrote up a solution to this problem had one too many. Yeah.
So the answer was back in the book for number 3 isn't the right one, right?
Actually, a little bit. Everything is a different problem. Let me make sure. 10 point. Okay. Yeah, because here we're using a sine transform.
And like it also doesn't have the like alpha squared in the exponent. I wasn't sure if that was intentional or not.
Oh, okay. So the original problem did have.
Yeah, it had alpha squared in the.
Yeah, that's also a mistake.
Okay, just wondering. Yeah. It did mine didn't match up, so I was confused.
Yeah, so the answer in the back is useless. Unfortunately. Well, so since the answer in the back of the book is not really available to you, if, you're welcome to, before you turn the assignment in to check with me, and I can check myself. Okay. I think I said that, yeah, so sometime on Wednesday, like certainly before 5 p.m. or so, is when the test will be posted. And then you'll have till 11:59 Friday to complete it. So more than 48 hours. I guess it's like 55 hours.
And we won't have class that day?
Right, classical does not meet that day. Or next Monday because of Mardi Gras break. So yeah, I won't see you again until the following Wednesday. I guess it's March 2nd. So, any remaining questions on either about the test or about homework?
Can we look at lesson 12, number 1?
12:1. Okay.
Yeah, so I got like 0 for my answer, but like
Oh.
the book answer had something different, so I was confused.
Yeah, okay, so, yeah, so what's gonna happen is, so you're writing the integral, okay, so and this is, you're finding the Fourier transform, so this is the whole real number line. Okay, so if I go to the table, okay, so this is the Fourier transform that you'll be using. So first, well, the comment I made on a previous problem applies here, that your function is 0 for positive x. So you'd be integrating from minus infinity up to 0. And then for that, you would substitute in your given f of x. Was it e to the x or e to the minus x?
It was like f of x?
Yeah,
e to the negative.
Yeah, e to the negative x.
but, and was that for negative or positive x?
No, negative x. Oh wait, for like the, I think it was for positive x, yeah.
Just positive.
That's really, okay. Well, something seems awful about that. Oh, okay, there is an answer in the back, but, let's see what that says. Oh, wait,
I got the answer from the appendix. Well, I guess what I assume that they asked us to check it against the.
shoot, wait, problem 1 or problem 3?
Number 1.
Oh, okay, oh, it wasn't, okay. Oh, okay, look, you talk about, okay, I think I see what the problem is. So you checked it against this.
Yeah.
Okay, and,
I think you could like integrate it from negative infinity to infinity. You said try to do it from 0 to infinity.
okay, oh. Were you using, as far as rule from the table that you used, was it this one?
Yeah, I just use like 1 for a.
Yeah, but the problem, this one doesn't apply because here, this function is non-zero on the entire real number line. The given function is 0 on half the domain.
Okay.
Now, there might be another rule that, okay. Oh, actually, trying to see if there's something for covering a piecewise definition.
I think there was one up where 13. No, that's actually x times.
Yeah. It is possible to make a rule like that, but they didn't bother doing it here. Okay, so I go back to the problem statement. Oh, wait. Oh, okay. For positive x, it's the final. So this way of running is really weird. I don't know why they did that. Okay, so you're integrating from 0 to infinity. Yeah, I just misremembered which half the function was non-zero on. And then you'll fill in e to the minus x for the f of x. And okay. Well, this doesn't actually fit the situation. It doesn't fit anything that's in the table. That's a problem. Okay. Whoops. Okay. There is a way to check, but it's a bit to pardon the pun, convoluted. Because what you're integrating based on this table, okay, 1 over square root of 2 pi, integral from 0 to infinity of e to the minus x, and then times e to the minus omega x. If you were to write the e to the minus I omega x in terms of cosine and sine, that would be the same as cosine omega x minus I sine omega x. And you break it up into two integrals, so one involving a cosine, one involving a sine. Now, it's not necessary to do that to evaluate the integral. However, then what you would have is a linear combination of a Fourier cosine transform and a Fourier sine transform that actually do show up in the table. So that it would give you, using this rule, so number 3 in the sine transform, and also number 3 in the cosine transform. So it gives you a way to check. It's kind of tedious to check, but yeah.
You want to do that for the number 1 then?
Okay. Actually, you know what? Well, first we'll see if anybody else has any other questions. I'll put this on a new page. All right, so lesson 12, problem 1. Okay, so what you have is your Fourier transform of your given function f of x turns out to be, so using the definition of the table, is 1 over square root of 2 pi. Okay, do this as an equation array. Okay, so 1 square root of 2 pi, integral minus infinity to infinity f of x e minus I omega x dx. All right, but because the function is 0 for negative x, I'll just cut that part of the integral out. So now we're going from 0 to infinity. Okay. All right, so what we're providing is just in general case how to express the Fourier transform of a function that's 0 for negative x in terms of a Fourier sine and cosine transform. So now this I will express the exponential in terms of the sine and cosine. Okay, and then I will break this up into 2 integrals. All right, so I'll have minus I, okay, sine omega x. And what you can see here is that if we compare these two, to what's given in the table for Fourier sine and cosine transform. Okay, so what's the definition? It's, okay, here, 2 over pi integral from 0 to infinity f sine omega x, and then same scaling constant for cosine, 2 over pi. But we don't have 2 over pi. We have 1 over square root of 2 pi. So what I will do is throw in a 2 over pi, as long as I also throw in a pi over 2. Okay. So that was a situation like this where I don't have what I need in the equation, so I just put it there, as long as I appropriately compensate for it, so it cuts down on mistakes. Okay, now let's simplify this a little bit. So we have pi and up top square root of 2 pi down below. And then we also have a 2 to the square root of 2. So I'll have square root of pi up top, 2 square root of 2 down below. That gets rid of pi over 2. And then same thing in the upper fraction. Okay, so now look at what's left. 2 over pi, integral from 0 to infinity, f times cosine. Well, that matches this exactly, so that is the Fourier cosine transform. Okay. That would be, whoops, okay. Okay, so for a cosine transform of f, and then over here we have sine transform. Okay, so what you can do is, so there's two ways to do this problem. Now, how I really want you to do a problem is just evaluate this integral directly. How you can check that is use the tables for the cosine and sine transforms to get these, and then multiply by the appropriate scaling factors and simplify, and see if that coincides when you get just by evaluating this integral. Onto it. Alright, so any further questions about this one? Or any other one? Okay. Well, good luck on the test when it comes out. Look forward to grading them over weekend. Okay, that's a lie. I never look forward to grading, but so.